Now, in this video, we're going to look at some of the similarities and differences between permutation tests and bootstrapping. A lot of the sort of analysis is going to be somewhat similar. A lot of the code is going to be somewhat similar, but the interpretation and a few of the settings are going to be a little bit different. Permutation tests are a way of conducting hypothesis tests without making a lot of distributional assumptions, so they are also considered non-parametric tests. But it is a way of essentially looking at the data that we have available to us and just making assumptions about that data that we have and not things like it's normally distributed or things like that. So we're going to start with an example of some data that tested whether on some guinea pigs, whether orange juice or synthetic vitamin C supplements did a better job on their teeth, essentially. So we're going to load a package in for our sampling that we looked at in our previous, a few lectures ago about when we did our first sort of bootstrapping example. We're going to use this for sampling from our data. And so first thing that we're going to do is we're going to input our data that we're going to use. And we're going to start with a vector form. All right, so once we have our data, we're going to start out by calculating the original mean. So this is the original difference of means between the two variables. So mean X and mean Y. So the original difference of means is 5.8. And then we're going to convert this into a data frame. Now, in this case, we're making two columns for our data. One is called the source, which means it's coming from our first set of data or our second set of data. And then the measure is just the measurement for that, the values from our vector. And then we're going to combine our two data sets together using rbind. And if we want, then we can actually look at our data. And you can see this was the data from the first column of vectors. This is the data from the Y variable, and they're now in a nice data frame. Sources are in their column by themselves. Now, similarly to what we did in the bootstrapping video a couple of lectures ago, we're going to calculate a set of differences. And so we're going to want to store those in a vector. So we're going to create a vector that we can store stuff in. And we're going to set how many simulations we're going to do. We're going to do 10,000 of them. Of course, you can also do this in scientific notation. So 10 to the fourth would also be fine here. N equals 20. And then we're going to do our for loop, I in 1 to n. And we're going to sample. And this is what the sample n function is what we need the dplyr for. We're going to take from our data n times, replace equals false. Now this is the distinction between the bootstrapping and the permutations. When we take the sample for bootstrapping, we make two changes here. We replace equals true so that we can resample the same data again. And the sample size that we're taking each time does not have to be the same size. So when you do bootstrapping, you can make it a smaller size or you can make it a larger size, and you're allowing replacement. In permutation tests, you have to take exactly all of the data. It has to be allocated someplace. And you do not allow replacement because it's a permutation, so no repetition. And then we're going to take the first 10 values of our data set that we just collected, and we're going to calculate the mean of the measure column, but only the first 10 values, because that's going to be, in the permutation test, we're essentially dumping all of our data into a single data set, and then we're saying, if these were all from the same population and we sampled 10 of them, and we take the mean, and then we take the other 10 that are left, and we take the mean of that, what are the possible means that we can get? And then how likely or unlikely are we to get the mean that we actually had under that assumption? So here, again, we're just taking, we sampled all of the data, but then we're going to take the first 10 to put in group 1, and then we're going to take the next 10 to put in group 2. So that'll be mean 2. And then this will be 11 to 20. And then our difference of means are going to be mean 1 minus mean 2. And then we're going to tack on those differences to our collection, the vector we're collecting those differences in. Again, the first time through, the vector is empty, so it'll just be the one value, but then each time afterwards, this will keep appending those new difference calculations to our vector. And now we can go ahead and we'll just run this. And it'll take a second. 10,000 is more than 1,000, which we were doing before. There we go. And so now we can actually convert our differences into a data frame, and we can filter it in order to find the ones that are different than our original mean. So I'm just going to call this diffs1, data frame diffs. And I'm going to set aside the ones where the diffs column has the variable greater than or equal to our original mean. And then our p-value for the permutation test is essentially going to be the length of this set of values that where the differences are bigger than our original mean, divided by the total number of samples that we took, the total number of simulations. And then we can print out the p-value. And here the p-value is 1 times 10 to e to the negative 4. So essentially there was 1 in 10,000. So basically there was one thing in our data set that had that value, 33 observations of one variable. Yes, and so that 1 out of 10,000 kind of confused me, and in fact, that is because that was calculating the number of variables, and we actually saw this in the very first video, that when you do length of a data frame, that if you're not careful about the specifying a column, it's actually going to count the number of variables, not the number of values in that list. And so you do have to actually specify length is the column name in that list, which is the diffs column, and then divide by n, and then the p-value. There's actually 33 observations in that k list. So 33 times did you get a mean that is greater than 5.8, greater than or equal to 5.8. And so when you divide that by 10,000, you don't actually get 1 out of 10,000, you get 0.0033, which is still less than any typical significance level, but it is not 1 out of 10,000. It is 33 out of 10,000 in this case. Now, we can also then, of course, sort our list in order to get our confidence interval. So diffs sorted. We're going to sort our diffs. And then we're going to take, since we have 10,000 observations, times 0.025 for 2.5% for the bottom bound, we're going to look at the 250th observation, and we're also going to look at the top one, the 97.5 percentile, 9751, 3.8. Now, the thing to keep in mind here is that this is under the assumption that that the true mean is 0, that these are all from the same population. So this is giving us confidence bounds on that 0 interval. The fact that our 5.18 is outside of that bounds is what tells us that we know that the hypothesis test is going to be rejected, that the 5.18 probably was not obtained from a case where both of these populations were equal. Now, you may want to, for instance, shift your boundaries from the center 0 to the center 5.18 in order to give some kind of an idea of what the confidence interval would be if it was centered at 5.8 by making that shift. But it's important to keep in mind what this confidence interval is, how it should be interpreted. So it's not a confidence interval around the difference of the means we found. It's a confidence interval around our assumption about the means having no difference. Now, we can do bootstrapping with the same data, and the analysis of our code is going to actually be very similar. And so I'm going to just copy a bunch of this and then make some small changes to it. So we're still going to start out for the bootstrapping case with our empty vector. We're still going to specify the number of simulations or samples we're going to take. We can change n to be something other than the sum of both data sets. So it doesn't have to be 20. It can be 10, it can be 50, it can be whatever. So I'm going to make it less just for the sake of argument. And then we're going to sample from the two different data sets separately. So we're going to have sample 1 and sample 2, and we're going to sample from data 1 and data 2. Remember, we converted our X and Y vectors to individual data frames, and we're going to set for the bootstrapping replace equals true. Because for bootstrapping, you want to treat this as sort of a representative, the data as a representative of the entire population. And so here we can, again, the n in this example matches the number of values in each of our individual data sets, but it doesn't have to. It can be larger, it can be smaller, it doesn't matter. It doesn't have to match where it does in permutations. And we're going to sample from the two of them separately because we want to calculate, again, if these were two different populations, then what would the mean likely to be? Mean 1, the sample 1 measure, sample 2 measure. We don't need to specify the intervals because they're not all in the same sample. And then the differences of mean 1 minus mean 2, and then that part doesn't change. So again, there's the permutations and the bootstrapping are similar, but the code is very similar, but they're not quite identical. And so if we run this, and I will also just sort of mention, you do have to make sure that you do empty your differences vector, or it will just keep adding on. And then when it's done, we can actually build our confidence interval for this data, basically the same way that we did for the previous example. But here we're under the assumption that these are distinct populations. So we should expect that this one is centered around the 5.18. And so you can see that we get bounds of about 2.2 to 8.25. So it's about 3 or so in either direction. So these values are somewhat similar to what we were getting from the permutation confidence interval widths. And again, there is some randomness going on here. So if you want to make these fully replicable, you should set a seed at the beginning of all of this. And I have not done that. So your numbers may differ somewhat slightly from mine. And then we can also calculate the p-value much the same way that we did before for our hypothesis test. And again, the code is going to be somewhat similar. So I'm going to copy and paste this and then make some tweaks to it. So we're going to create our data frame from our differences, but I'm going to do it from the sorted ones. Not that it really matters that much. We're going to find our K value. We're going to filter where our differences sorted is less than or equal to 0. So again, comparing to our null hypothesis is that there's no difference. And then we're going to take our length of the differences sorted column. because the vector name becomes the column name when we convert this to a data frame. And then we can calculate our p-value the same way we did before. So let's see what happens. So in this case, our k, if we can find it in our list, there's k. There's only 2 observations that are less than 0. And so this is 2 out of 10,000. So the p-value, the likelihood of getting a difference, just, again, from bootstrapping, assuming these populations are different, the likelihood of getting a 0 is extremely small. And we can find the minimum. And sometimes you may find that there, in fact, are no values that are less than 0 when you do this. Again, there's a certain randomness to it. I have run this code before and gotten no negative values whatsoever. And so then you can calculate the minimum that's actually just above 0. In this case, there are 2 values that did come out to be 0 in this particular run of the data.